We tend to think that our library is not haunted any more so than the elevators are, but I've been in the elevator. All right, so let's continue with our examination of double integrals. As you saw in the recording for last Friday previous, we did double integrals on rectangles that looked like this. So I have an integral from A to B and an integral from C to Z, and we turned the double integral into an iterated integral. The integral from A to B and then C to D. But C to D is in Y, so this is dy then dx, or we do it the other order. Dx, dy. And we can think about this because we make our little towers. I showed you the little plastic sculpture for our monkey saddle on the video. We can think of whether we make the towers first by going across, then up and down. That would be dx first, then dy, or first going up and down and then going across, dy dx. But this works perfectly well. Fubini's theorem here turns a double integral into an iterated integral because the boundaries are so nice. What happens if I want to do an integral on some weird region D? Well, now I have a problem because I can't do the same thing because I don't know the way to turn the edges correctly. So what I could do is I could kind of embed this inside some rectangle. Maybe put a rectangle around the outside and a rectangle around on the inside and start doing comparisons. And I'm not sure that's a good idea because my function might not actually even be defined outside this particular region. So in order to do this, we have to have nice boundaries for D. But now I have to determine what's it mean to be nice here and what kind of regions are nice enough to work in. And it depends on the way D is shaped. So instead of working on a rectangle, if I want to work on this awkward looking weird region, I need to try and know some things about it. But let me go back to the way I thought about the rectangle. When I was looking at the integral dy dx, I said what we really do is we go up and down first, and then we go left to right. So what if I had a region that was bounded above and below by equations? A region that looks like this has some function of x across the top, some function of x across the bottom, and goes from left to right by numbers. So this region would look like this. That's not really a rectangle. I don't know what the bottom equation is. I don't know what the top equation is. But a region that looks like this, I'm going to call this a type 1 region. And I claim that I can take Fubini's theorem and apply it here. And I can think of moving our little towers to make the differentials. I'm going to go up and down first, and then I'm going to move that object from left to right. And as I showed you on the video, we had these pictures here on page 994. It looked like this as we moved across our rectangle. First we went in the Y direction, and then we went in the X direction. And what we really did when we went in the Y direction, we turned everything into a function of X. And then we made the slices like we did in chapter 6, where we sliced up volumes of rotation to make little slices of bread. It's the same picture. I'm going to do this with this region. And when I do that, the benefit is that because these things are in terms of X, when I integrate with respect to Y first, my resulting integral has no Y's in it. I turn everything into X's. An example. Here is a type 1 region. It is described in X with a pair of numbers and in Y with a pair of equations. Although the way I've written it, it doesn't look like it's a pair of equations. But let's think of this as function of X, and this is function of X. Let's graph those two functions of X. G1 of X is minus X, and G2 of X is positive X. What's that graph look like for each of those? That's Y equals X. Y equals minus X. Okay, great. Now, specifically, I only want the parts of those lines between 0 and 2. So the line Y equals minus X has a slope of -1, but I only want to start where it's 0, and I only want to go to where it's 2 along the x-axis. Similarly, with this line, I only want to go from 0 to 2. This is my domain D. So I would like to do an integral. I would like to do the double integral over this domain of x cubed y squared dA. Now, other than the fact that that's a nasty ass looking function, I still should be able to figure out what this does. My thought immediately, because this has a function on the top and a function on the bottom, I'm going to think about going up and down the y-axis first, and then moving that from left to right. So I can think of, I'm going to build this x function, and then I'm going to slide x from 0 to 2. That means this setup right here is enough to tell me that this is type 1. Try to write this dy dx. So I say to myself, I'm going to put the boundaries in y on the inside integral. And I'm going to put the boundaries for x on the outside integral. So instead of dA, now I have a dy dx integral. And then this function stays exactly the same. So I've used the same idea as I did in Fubini's theorem. Only instead of having numbers on both my iterated integrals, my inside integral has functions in the variable of the outside integral. Why would I do this? Because I'm a sadistic bastard. Well, yes, but there's a better reason for that. I'm going to do this integral first. I'm going to do the integral in y. If I'm doing the integral in y, I'm integrating y squared because x cubed is a number. We just leave it there. So what's the integral of y squared with respect to y? Antiderivative, not derivative. Got to go the other way now, right? 1/3 y cubed. So the x cubed stays there, and then I get 1/3 y cubed, and that gets evaluated between minus x and x. But I still have this on the outside. Here's my advantage to doing this way. Evaluate that for me and tell me what you get. Just the stuff in the parentheses. Because I get a 1/3 x cubed, and then I get minus a 1/3 negative x cubed, but that negative, when cubed stays negative, so that becomes positive, I get 2/3. But there's a 2/3 x cubed and there's another x cubed, right? So that really becomes 2/3 x to the 6th. Aha! The inside of my integral has nothing to do with any variable other than x, and I'm integrating with respect to x. I've taken what was a double integral and iterated the single integral to simplify it to one variable. I can do that integral too. That's a piece of cake. The antiderivative of 2/3 x to the 6th. Evaluated from 0 to 2. When I put in 2, I get 2 to the 7th, which is 128. Multiplied by 2 over 21, I get 256 over 21. The distinct advantage to being able to determine, hey, this region is type 1. This always works for type 1 region. This is in a box on page 1002. Now, this works when f is continuous. All of our antiderivatives only work when our functions are continuous. So I'm going to make that claim all the time that I'm dealing with continuous functions. So the real kick here is to figure out what our function is. I'm sorry, what our region is. What's the boundary, top and bottom? What's the boundary left and right? Questions? Rectangles are easy because they can be done in either order, independently of what f is. But as I said in the recording, sometimes one method is easier than the other based on F. But now I have to look at the comparison between F and the region. This only works if my region is defined up and down by a boundary on the top and a boundary on the bottom. So what happens if it isn't? What if my picture is turned sideways? Well, now that means that the left and right edges are bounded in functions. That means X is going to have a function to the right of it and a function to the left of it. X equals h1 of y, and X equals h2 of y. So now my functional boundaries are vertically oriented rather than horizontally oriented. But now my y values are bounded by numbers. This is the exact same idea, just flipped. Vertically oriented instead of horizontally oriented. Matter of fact, the picture even looks similar, right? Instead of a curve on the bottom and the top, I have a curve on the, well, turn your head sideways. A curve on the bottom, a curve on the top. Lower X values, higher X values, right? I would think turning the picture this way, right? Lower and upper. Smaller X's, bigger X's. But if that's what I'm going to do, then I can think of the way I move through this region to say what I'm going to do is I'm going to move this way first. I'm going to move from left to right first, which means I should be doing this dx, dy, instead of dy dx. This is a type 2 region. So here it is more my region that tells me whether or not I want to integrate with respect to x first or with respect to y first. Sometimes one of them is markedly easier than the other. But sometimes it really doesn't matter. I'm not even going to do an integral. I just want to figure out which way to write this equation for the boundary of this region. So what I want you to do is I want you to draw me a picture. What's the picture of this D domain? picture look like? And then not to scale, right? I didn't even put marks on the X and Y axis, but that's the domain right there. That's D. Now, given the fact that I already have equations y equals, my immediate reaction is, hey, let's do this as a type 1 region. If I wanted to describe this as a type 1 region, then you would need to write y bounded by functions and x bounded by numbers. So I asked you, what are the appropriate functions for the lower bound and upper bound? What are the appropriate constants for the left edge and the right edge? I have to make them equal to each other to figure out where these two things cross, right? Okay, they cross down here at 0, 0, and they cross up here at 2, 4. Because if I have x squared equals 2x, I move that over, I get x is 2 and x is 0. Great. How do I fill in the rest of these inequalities here?
You put function in the bottom? So the x squared less than y is less than 2x?
Because this is the one on the bottom, x squared, and this is the one on the top, 2x. And then, exactly. But there's no requirement that I do this as a type 1 region. And depending on F, it might be better for me to do this as a type 2 region. I don't know in advance. So let's figure out how to do this same picture going the other way. Well, now these are functions and these are constants. By the way, that's part of why I always write them vertically rather than next to each other. The top line is the functions, the next one is the constants. Problem, as written, up here, I can't just move those things down here. What do I have to do? I have to change my equations. So this equation right here, what's it get rewritten as? And this one? And because I'm on this side, I want the positive square root. So now, which of those is the left? Which of those is the right? Thank you, Yana. That's what I do every time. I tip my head and I look at the picture, which is the bottom, which is the top. That works for you, right? If I look at it sideways, then I'm coming up from the y-axis. What do I hit first? I hit the line. So the line is the left curve. And the parabola is the right curve. The bottom and the top, as it were. How about my numbers? Unfortunately, no, they are not the same because now I'm measuring my distance vertically. This is in y, so I have to use the y coordinates. It's the same points, but I have to use the y values of those points instead of the x values. Now, before you freak out on me and go, I've never ever done like this before. Yes, you have. Don't panic. But here, back in Calc 1, we did the area between curves back in chapter 6. And we were given this picture right here. And on this picture, we have a sideways opening parabola and a line. If I do this as a type 1 region, I actually have to do it as two separate type 1 regions. I have to do it as a type 1 region here, where the bottom and the top are both parts of the parabola, and a different type 1 region here, where the bottom is the line and the top is the parabola. And that's really messy because that means I have to take this equation, y squared equals 2x plus 6. I have to write the positive square root and the negative square root. But if I turn it sideways, then I can write this as a bottom x and a top x. So I know it's been quite a while because this was the end of Calc 1. That was a while ago. So we did this. And as a matter of fact, in this section, they bring exactly that same picture back. There's the same thing on page 1004. The exact same region done as type 1, you've got to do two separate parts. Done as type 2, you only have to do one part. So it's much easier to do this as a type 2 region than a type 1 region this time. Sometimes it isn't the region that's the problem, but it's the function that's the problem. As written, is this type 1 or type 2? Because it's dy dx, it's type 1, exactly. So I'm going to integrate with respect to y. How do you integrate sine of the quantity y squared? I don't know how to do that. If I really want to go back and dig through a crap ton of trig identities, I might be able to find a trig identity that could turn sine of y times y into something else. You remember all those trig identities? Me neither. I don't want to do that. That sucks. On the other hand, if I tried to integrate this with respect to x, what would happen? Sine of y squared is a constant in terms of x, right? So I could actually integrate with respect to x a lot easier than I could integrate with respect to y. Problem is that I don't know what the new limits of integration should be if I want to switch this from dy dx to dx dy. So I need to know how to switch. And I am personally of the opinion that the easiest way to switch is to draw the picture and then figure it out like you were starting over. So these limits of integration are y is between x and 1, and x is between 0 and 1. Let's draw the picture that goes with that. My top line is functions. So I need to graph y equals x. I need to graph y equals 1. Fortunately for me, those are both straight lines. It's the graph of y equals x. And the graph of y equals 1, horizontal line. So now I get to ask you the question, where is our region? It's the triangle here. This is written as type 1. Now I basically want you to ignore that and give me this region as type 2, which means we want x's up here and y's down here. And Ben, that's exactly what I'm doing in my head. I'm turning my head sideways to try and figure out what's what. What's the left edge equation? Exactly, the y-axis, x equals 0. What's the right edge? That's this line. I have its equation right here solved for x. Now, I need a number that's the lowest y value I'm allowed to use and a number that's the highest y value I'm allowed to use. Because I go from down here to up here. And now that means I can take this same function, sine of y squared, and do the integral dx dy like that. And I'm about to make your day. What happens when you integrate with respect to x? I just get an x. But that x is evaluated on those limits. What do you get when you evaluate in there? I get a y. And then I have an integral in one variable. How do I do that? Product rule and integrals would be integration by parts. I'm not sure I like that. I could, but there's a much easier way. u equals y squared. Then du is 2y, and I have the y on the outside. Aha, aha. If u equals y squared, then du is 2y dy. All I'm missing is the 2. You just have to make an executive decision. What are you doing with the numbers? Are you going to change the numbers to u, or are you going to leave the numbers in y? It's completely your call. Then I'm going to write down here, I'm going to write y equals 0 and y equals 1. What's the antiderivative sign? Okay, so I get negative 1/2 cosine of u, y equals 0, y equals 1. I got to go back, minus 1/2 cosine y squared from 0 to 1. Minus 1/2 cosine of 1 squared minus negative 1/2 cosine of 0. What's cosine of 0? Ta-da! Oh, I forgot the 1/2 there. 1/2 cosine of 0. If you want, you could put the 1/2 out front in parentheses around the whole rest of it, but well, yes, I could have used integration by parts, but a u sub was a whole load easier. So now there are two things to weigh when I go to look at a double integral. If it's not on a rectangle, I need to decide, is this type 1 or type 2? Based on the way the function is given and the way the domain is given. So I need to look at the domain and say, this is given as type 1. Look at the function, does it work for type 1? It doesn't work for type 1. Will it work for type 2? If I reversed the order of my integrals, would it make my life easier? Then I go back to the region and say, can I make this region type 2? Question. If it doesn't include the actual boundary, then we've been given an open region, right? So imagine we were doing a definite integral that went from 0 to 1 but didn't include 1, right? We'd have to be doing some sort of improper integral, wouldn't we? I could bring improper integrals into play here the same way. I'm just not sure it's worth it at this point. But yes, it could be less than or greater than, but not equal to, in which case all of a sudden I know I'm going to have to do a limit in an improper integral at some point. I don't want to do those right now. It also turns out that we have the same rule we have for single integrals. We did single integrals, we could say, oh, if I'm going to go from A to B, I could go from A to C and then C to B. So there are a lot of similar properties that we had for single integrals that carry over exactly the same way. Properties. If we have the double integral over some domain of f plus g of xy dA, that's the double integral of f of xy plus a dA plus the double integral of g of xy dA, both over the same domain. So if you're adding, just add. Do each integral separately and then add. If you've got a constant in your integral, you can take that constant out front. Those are exactly the same rules we used in Calc 1. I'm really happy to see those come up again. The monotone policy works. If f is bigger than or equal to g, bigger than or equal to 0, then the double integral over the domain of f dA is bigger than or equal to the double integral over the same domain g dA. If you integrate a bigger function, then you get a bigger answer. My overlap idea. Suppose D can be rewritten as D1 union D2. Where D1 and D2 have no overlap other than the boundary. Well, then the double integral over D of some function is equal to the integral over the first domain plus the integral over the second domain. And that's what allows me to think about just using the edge as the problem edge, because I could say, oh, well, we could go up to the edge and then another piece, right? So the edge really only counts once. There are a couple of ways to extend this. Yes, they will mess up there occasionally and sometimes just hang out up there. There are several extensions to this idea. As a matter of fact, if you have a region that is made up of a bunch of different pieces that don't overlap, you can extend this from 2 to 3 to 4 to 17 to however many you want. It is even possible to extend this idea to infinitely many regions. What happens when you integrate a constant? Okay, wait a minute. I'm not even going to do this by calculus. I want you to draw your region in your head in the XY plane. And I want you to think of the function whose height is 1 everywhere. Doesn't that just make a slab? The volume of that slab is the base area times the height. But the height is 1. So the volume is just the area of your region times 1. So the integral of 1 is the area of the domain. As a matter of fact, we can think of this idea as bounding by slabs. By the way, this picture appears on page 1007. Something whose height is 1 is a prism. And the volume of a prism is base area times height. If I have a number that's smaller than and I have a number that's bigger than my function, I can bound that the same way. If m less than or equal to f of xy less than or equal to capital M for all xy in my domain. Sorry, I just realized I used that symbol without thinking about it. That upside down capital letter A means for all. Some of you haven't taken discrete math and might not have seen that symbol before. Then M times the area of D is less than or equal to the double integral over D of F is less than or equal to capital M times the area of D. My function must be between this slab and this slab. Then the volume must be between the slab of the prism on the bottom and the slab of the prism on the top. Questions? I'm not actually going to do this problem, but I want to set it up. So my first question is, how should I set it up? dy dx or dx dy? I'm going to take out my 2x4 because none of you are doing the thing that you absolutely need to do. Draw the picture. You can tell me what the equations are once you look at the picture. The vertices of my triangle are 0, 2, 1, 1, and 3, 2. Should we do this type 1 or type 2? Why? There's a straight line boundary on the top, isn't there? And there's a straight line boundary on the bottom. Well, technically it's only a point, right? So the top and the bottom can be bounded by numbers. And if the top and the bottom can be bounded by numbers, 1 less than or equal to y less than or equal to 2, then if I can figure out what the equation for the left line is, what the equation for the right line is, and write those lines x equals, I'll have a left side and a right side. But I have 2 points. For the left line, I have the point 0, 2 and the point 1, 1. That's a slope of -1 and a y-intercept of 2. I know this line right here is the line y equals minus x plus 2. Which means I can rewrite that and I can get x equals minus y plus 2. Just switch the sides, right? Move the x over to the left, move the y over to the right. Once you come up with the equation for this line, you've got the same thing. This has a slope of 1/2. We went over 2 and up 1. So its intercept should also be 1/2. Because if we back up 1, we'll go down 1/2. Wait a minute, I need to rewrite that to be x equals. So I multiply by 2, and I get 2y equals x plus 1. I get x equals 2y minus 1. Now I have a left edge and a right edge. Much easier to do as a type 2 region. You could do it as a type 1 region. It is a type 1 region. You'd have to do 2 of them. Because you'd have to break this up right at that corner so that you had a left region and a right region that didn't overlap except at the boundary. Ready? I would like to do an integral on that region, the region between 2 circles. That's not type 1. That's not type 2 either. Well, technically it is type one, but in order for me to do that as a type one region, I have to break it up into 3 pieces. And in order for me to do it as a type two region, I'd have to break it up into 3 pieces, and that just sucks. I don't want to do that. So Monday, we'll figure out how to do that for you. That'll be easier. But that's for Monday, because tomorrow is the exam. You are entitled to 2 note cards. The one you used on exam 1 and a new one. You'll have to turn them both in with the exam. That's why I gave them to you little paper clips, so you can put them back in the same way. If you need note cards, follow me over to the enrichment center at 2:30, or go now, and they have a snack. All right, I will see you all tomorrow. Have a wonderful rest of your day. I'm gonna post the review keys and the homework keys in about another minute and a half. I just have to turn all this stuff off first.